What is the continuity equation for an incompressible fluid? So I'd like to first talk about the continuity equation that was listed on the key concept slide. Rho 1 V1 A1 equals rho 2 V2 A2. So where does that come from? Let's say we're in a region where there's some amount of fluid flowing, and maybe it's in a pipe. So I'm just going to draw a pipe here. That's easiest to think about. But this pipe could be just like, say, part of a stream or part of some other kind of fluid flow happening for whatever reason. But again, a pipe with definite walls and therefore boundaries is the easiest to imagine. And let's say I look at some cross-sectional area here of the pipe. We'll call that one A1. And in a certain amount of time, we'll say delta T. Let's say the fluid goes this far. Okay. And so what do I mean by that far? Well, by the rate equation, that far should be equal to whatever the speed of the fluid is going right there multiplied by that delta T. So I'm going to say V1 delta T is how far it goes there. Now, it might make sense that when the pipe widens, the fluid might slow down. So if here there is a cross-sectional area A2, it might go a little less far in the same time delta T. And so that distance there would be V2 delta T. But if I claim that the same amount of mass flows past a point in the pipe in a certain time delta T, regardless of where you are, then if I go over here and I say, well, what would that mass be? I'm going to say M would be equal to the density of the fluid multiplied by whatever volume corresponds to sort of the region between these two dotted lines I drew. And I would write V for volume, but we've already got V for velocity, and I'm worried it's going to get confusing. So instead, I think what I will do is just express that volume as the area multiplied by that distance it went, which is V1 delta T. And so that's for, again, that one section, but we're saying that should be the same amount of mass that passes in a time delta T for the other section. And for the other section, we're going to assume the density there is rho 2. So I didn't, maybe I should have labeled it here somewhere, right, that this section is rho 1. We're assuming this section is rho 2. Okay, there it is. And then so it would be density times volume again, but in this case, the volume would be area 2 times that distance, which is V2 delta T. And so those two are equal to each other. If you cancel the delta T's, that gives you the result of rho 1 A1 V1 is equal to rho 2 A2 V2. And that's how you get to the continuity equation. It really has to do with conservation of mass. We're saying there's no mass leaking out anywhere. If a certain amount of mass passes a certain spot at this point in the pipe in a certain amount of time, that same amount of mass is going to pass a different spot in the same amount of time somewhere else in the pipe because it had nowhere else to go. So the amount of mass going per time should not be different. But the question we have here is, what is the continuity equation for an incompressible fluid? Well, an incompressible fluid would have the property that these two densities have to be equal to each other, because if the fluid cannot compress, that means the amount of mass per volume should be the same throughout. So that equality would imply that we could just cancel out the rho 1 and the rho 2, and what we would be left with is A1 V1 is equal to A2 V2. Let me make that 2 look slightly better. So let's go ahead and check that with the slide, and that seems to be right.